Welcome in everybody to our next N3AS seminar of this lovely summer. And today we're very happy to be joined by Professor Anna Watts from the University of Amsterdam. And we'll be hearing about NICER and its view of neutron stars. So please, Anna, when you're ready, take it away.
Well, thank you very much. And good evening from Amsterdam, in fact, Utrecht, slightly outside Amsterdam. Yeah, it's a pleasure to talk to you a little bit about NICER, what we've done so far, the things that we're busy with at the present time. And I realized slightly to my horror just before the talk that I did not have a picture of NICER anywhere in my talk. So I've hurriedly put one in the background. So NICER is this tiny little white box that you can see just here above my shoulder on the International Space Station. And it's an X-ray telescope whose primary goal is to explore the nature of matter in the cause of neutron stars. And of course, being a NASA mission, we have this nice mission patch basically along the way as well. So the loop of logic essentially that NICER exploits is to basically say, we have unknowns in dense matter physics down at the bottom left of the diagram here. We don't know what the precise composition is of dense matter in the cause of neutron stars. Is it neutron rich? Are there hyperons? Are there deconfined quarks, for example? Nor do we know fully what the forces are between those particles. But all of that microphysics sets on the larger scale the equation of state, pressure density relationship. Now, of course, in theory, I should put temperature in here as well. But NICER deals primarily with old cold neutron stars. So for now, I don't worry about temperature. But of course, if you wanted to extend it to newly merged or newly born neutron stars, you would need to put temperature in there as well. Various different possibilities for equation of state models computed in various different ways. But those equation of state models are then an ingredient in the stellar structure equations and set essentially on the larger scale the mass radius relationship, which you can generate for a given equation of state by essentially solving the TOV equations or their rotationally modified equivalents. So I still need to try and find something that as astronomers we can go and measure. But the mass and the radius and also the spin rate of the star determine its exterior spacetime. And this is a relativistic space-time where relativistic effects are important, strong gravity, very high rotation speeds of several hundred times a second, so the surface of the star moving at an appreciable fraction of the speed of light. So basically, any photon that leaves the surface of the neutron star has to propagate towards us through this relativistic space-time, can in principle pick up imprints of relativity, hence mass and radius. We can potentially measure mass and radius that way and then track the whole way back around this loop. And that is the start point from which NICER begins. In terms of the actual data that we are trying to use to model, we're talking about X-ray emission essentially from the surfaces of neutron stars. NICER looks at what are called rotation-powered millisecond X-ray pulsars. These are old neutron stars. They've been spun up by accretion from a companion. And they re-emerge as millisecond radio pulsars. So they're also emitting the radio, but the return currents in the magnetosphere heat up the magnetic polar caps as well to X-ray emitting temperatures. And so we get these bright X-ray emitting hotspots, we think, on the surfaces of these stars. But they're X-ray, but they are not accreting. And that's also very important. So this is the kind of data set here that NICER is actually collecting. And that we are trying to model to get at the dense matter physics. So what are you seeing here? This is what we call a pulse profile. So basically what we've done, you're seeing here effectively two full rotational cycles of the star. This is the first source that we analyzed on the left, and this is the second one that we did on the right. Basically what we do is we watch the pulsar for a very long period of time. So we build up data, over the course of about a year or so, or now even longer. Observing it as many times as we can. These are very stable, very boring sources. And as the star rotates, the brightness of the emission changes and the spectrum of the emitted radiation changes. So every photon that we get, we drop it in a box of energy channel. So that's the photon energy that we measure. And also the rotational phase point of the pulsar at which it arrived. So when in the rotational cycle. We drop it into a little box. And over time, we build up these things, which are pulse profiles. The brighter the color here, the more photons or X-ray counts there are. And what you're seeing at the top is what we call the bolometric pulse profile, where essentially we've added up over all the energy channels, but still kept it rotationally phase resolved. And you can see this star has a very very pronounced double peak profile. The one on the right, the data are a little bit lower quality, but it's a very interesting star for reasons I'll come into in a moment. And again, you can see a prominent double peak profile in the bolometric pulse profile. So those are the kind of data sets that we want to build up. And basically, those are generated and pick up enough relativistic effects in them when we try to model them, that in principle, we can extract mass and radius. So this is the analysis process that we run through when we get our NICER data sets. So basically, we are doing, again, a Bayesian inference process using a physical model for what's happening and simulating that, and then comparing it with the data that we have essentially from NICER. So up at the top is the pulse profile data that I already introduced you to. Photons basically sorted by energy channel in which they arrive, so the photon energy and the rotational phase cycle. I then need to have a physical model of what is going on in the star. So I'm going to build myself a model of an emitting neutron star. We understand extremely well, thanks to decades of work by multiple different groups, how to model the space-times of spinning neutron stars extremely well, taking into account all of the most important relativistic effects. So in our model, we have mass and radius that specifies the space-time. What else do we need to do to simulate data like this for comparison? Well, it depends on multiple different factors. One of which, of course, is how many hot emitting regions do I put on the star? What size, shape, and temperature are they? We don't know any of this a priori. We don't know where they're located on the star. We quite often don't know what angle we are looking at the star from, although sometimes we do have some constraints on that from radio observations. We'd like to know the distance to the star. Again, sometimes we have information on that from other means, which is helpful, and that sets the overall brightness that we see. There's also, for example, there can be a very thin atmosphere on the star, and that can also affect the pulse profile as well. There's interstellar absorptions. There are a whole bunch of other physical factors, some gravitational, some geometric, that would influence the pattern that you would see basically for a given choice of surface spot emission. Then, of course, you can simulate this, but you also need to compare it to data, which means you need to know how your instrument behaves and how would that affect the incident radiation. So we also need to have a model of how the NICER spacecraft behaves. I always say, NICER is perfect, but our understanding of it is not, and we need to fold that into our models as well. So this basically is the kind of simulation part of the machinery, that for any given choice of parameters, we can simulate something that looks like a pulse profile, basically for a given exposure time. And then basically during the Bayesian inference process, we compare that to the data, compute likelihoods using this model with priors on all the parameters, basically, and then we run through this huge statistical sampling process, and out of it pops at the end posterior probability distributions for the mass and the radius, which we're interested in from a nuclear physics perspective, and also all of the geometric parameters of the star as well, the locations and so on of the hot magnetic polar caps. If you're interested in going into the analysis in more detail, our pulse simulation and inference code, which is the simulation software and also all of the inference machinery, is actually available open source. The NICER collaboration right now has 2 independent analysis teams. It has my team based out of Amsterdam, and we have developed this software package, XPSI, which you can find on GitHub, as there's also a JOS paper as well if you're interested in playing around with it. This is our simulation analysis code. There is also an independent analysis team led by Cole Miller at the University of Maryland. They have their own code, and I'll go into some of the different assumptions and things that we make a little bit later on. But basically, for every data set that we've had coming through so far, both teams analyze the data independently using their own codes, and then we do cross-checks and comparisons to try and see if we can understand any sources of difference, and ideally at the end to arrive at consistent results and fully understand those. So that's why for every NICER result that you see, there are usually 2 analysis papers coming out independently from the 2 teams within the collaboration. And indeed, other teams will start to take part in that process as we go on as well. Okay, let me mention some of the very important ingredients that go into our modeling. One of the things that we have to include is a prescription for the surface pattern. Again, How many hotspots do we assume? And in the Amsterdam modeling, which is mostly what I'm going to talk about now, the XPSI modeling, we assume 2 emitting regions. We have to make an assumption for the shape and the temperature distributions that are possible, basically within those hot emitting regions as well. And ideally, we would go to a pulsar theorist and be given one perfect model that works for everything, and we would put that in and then infer those model parameters. Because of computational cost, what we actually do is we are inspired by pulsar theory. We take a look at the possible shapes that they generate, like these return current heating patterns, basically coming through the magnetic field of the pulsar. And we try and build simple parameterized models, essentially of the possible range of surface patterns that takes into account a lot of different possibilities. And then we work up through a sequence that gets increasingly complex. So just as an example, our simplest model would be to have, if we have 2 emitting regions, they're both circular single temperature hotspots. And maybe you allow them to have different sizes. They don't have to be directly opposite each other or antipodal on the star. They can have different sizes and temperatures. Then you can add complexity. You can add a core to that circle. So you've got a dual temperature region. You can allow the core to move around. And if you allow circles to overlap for each emitting region, you can make things like crescents, basically, and long, thin rings as well. So basically, this is the way that we've chosen to parameterize a range of different surface pattern possibilities. The Maryland team have their own slightly different way of doing this, of describing these basic patterns. But the idea is we encompass a whole range of possibilities from pulsar theory in the modeling that we do, and we infer these parameter shapes as well. So basically, NICER went up basically 2017, and it took us a while to get our first data set built up. Long period of collecting enough data. You need at least 1 million photons to be able to do this kind of analysis. So it took us a long time to do that, for then to us to run through the analysis pipeline, iron out the issues in the process. And we published our first results essentially back in 2019. For the first source that I showed you here, this is our second brightest source, and it's one for which it's not in a binary, so we have no information at all from radio pulsar timing about the mass of the star. Okay, so this is a completely blank source in terms of possible information that we have, but it's a nice, very clean double peak pulse profile that we're trying to model. So we wound through our detailed inference process. We built up through this more complicated model sequence. We do model comparison using things like Bayesian evidence. Looking at inferred astrophysical backgrounds, for example, in the modeling. And out of that process, you kind of determine a winner in your model space where you think the surface pattern is as complex as it needs to be in order to explain the data. And then from that, you infer then your mass and radius at that point. This is the geometry, basically, that we ended up inferring. 2 hotspots, one a kind of very long extended arc and one very small spot. Maryland team, using a different surface parameterization, inferred a very, very similar hotspot pattern as well, basically, which is extremely reassuring. So one thing you can say straight away, which is not related at all to the mass and radius, is that for a start, this lovely dipolar field structure that everyone knows and loves from their neutron star textbooks, that is not what we are seeing in this particular star. The magnetic field structure probably has to be something much more complex. Something a little bit perhaps like this. And so one of the things we're now working on is whether this kind of field geometry, which would set the polar cap locations, is consistent with the radio and the gamma ray emission. And so far that seems to hold up for this source. So that's a kind of interesting aside in terms of mapping the polar caps. We then moved on to a different source, which is the one I'm showing here on the right. This source was not on our radar when NICER launched because it hadn't been discovered, or at least its mass had not been measured. So PSR J0740 plus 6620 is the heaviest neutron star that we know. It's in a binary system, so the radio pulsar folks can get a good Shapiro delay measurement. And it means they can actually get a very good measurement of the mass of the pulsar and also distance and inclination, which is very helpful to us as well. So we're looking at this star almost directly along the equator, which is why they can make a Shapiro delay measurement. You can see the light bending in this little cartoon due to the relativistic effects coming out here. And again, the spots, this time two circular spots was a perfectly reasonable description of the geometry. We didn't need to go to more complex models to explain this one, and it didn't affect the mass and radius if we did. Particularly, they all stayed quite small. But they're again not opposite each other. They're not antipodal. So it's a more complicated magnetic field structure. But so this one, it came along after we launched. Because of the very high mass, we immediately decided we would try and build up a data set on it, because it's very interesting for dense matter. It's a faint source for NICEA. It's a real stretch to do it. But we were able to build up a sufficient data set to get a mass measurement, or sorry, radius measurement, which is what I will come on to now, and show you the two mass radius inferences that we have published so far. What I'm showing here, again, are the results from the Amsterdam group, the XPSI code, published in Riley et al. 2019 and 2021, led by then graduate student Thomas Riley. So you're seeing here 68% and 95% credible regions for the mass and radius, basically coming out of our code. They're about plus minus 10% uncertainty that we're getting. Here is the 0030 source, the source for which you had no mass prior. 0740 is the source for which we had a good mass prior, but the uncertainties end up being comparable because the data set is of lower quality because it's a much less bright source for NICEA's analysis. However, I wouldn't say necessarily that any mass radius relationship is ruled out so far, but you can see perhaps that it's slightly disfavoring some of these very, very soft things, basically down at the lower edge here. One thing that 0740 taught us was how important it is to have a measure of the background. What you see in your pulse profile, basically these peaks, they sit on top of a constant kind of background spectrum. And there are two ways of getting that background spectrum, or the constant, the kind of unpulsed piece that you sit on. One is just genuine astrophysical background, particles around the space station, other sources in the field of view, that kind of thing. And another possibility is that the star is very compact and there's such high gravitational lensing that you actually always see one of the spots, or it's perhaps up near the rotational pole. And so you can get an unpulsed component that way from the spots themselves. And disentangling this is quite difficult. And I see a question already.
Yeah, thank you. So on that plot, there's also a measurement or an inference of the mass from the Shapiro delay from the radio work. So where does that go on this and that purple band there?
Okay, so we use that measurement as a prior on our analysis.
Very good, thank you.
So basically, we take that into account. In fact, we take a joint prior on mass, distance, and inclination from the radio folks, who were very kind to actually revise their measurements for us. This was published in Fonseca et al. And to give us basically revised priors for all of those three parameters, which we use in our analysis. And essentially, the mass doesn't really shift from that uncertainty that they provide us.
Very good. So your mass radius relation is basically consistent with that.
Yeah, I mean, we take it as a prior and the data do not move anywhere away from the mass, and then we just constrain the radius.
Thank you.
Okay. Okay, so basically, background. It was tricky at the time to get good background estimates for NICEA, and it sits on the space station in this very high particle environment, and it's not an easy thing to try and model for the team. However, we also have data from XMM for this source. Again, not pulse data for the heavy pulsar, but at least XMM sits in a much lower background environment, and you can get a good idea of what the real background of the XMM observation is. So XMM provides you a nice way of saying, okay, how many photons in an XMM observation come from the source and how many come from the background, like sources in the field of view or something. So what you can do is you can actually simultaneously fit with your model, your beautiful pulse, gorgeous NICEA data set, and this kind of phase average data set from XMM that basically just says this many photons have got to come from the star, and the rest of them have to come from something else in XMM. So we do joint fitting to find a way of constraining essentially the background. And the effect of that in this first paper that we did basically back in 2021, you can actually see. These are some of our posterior probability distributions. Here's the mass, for example. The prior is in there as a dashed line in the middle, and you can see that the inferred mass doesn't really shift at all. Sorry, let me go back to this. What you can see, though, is when you just take NICEA on its own in blue, and then you jointly fit the NICEA XMM in red, the radius shifts up, basically, and that is because having a constraint on the background kills off essentially some high compactness solutions. So it tells you this is the compactness over here, that actually you're kidding yourself. You're trying to create unpulsed component from spots that you shouldn't be doing, because it really does come from other stuff in the field of view. So background estimates are really, really useful and made a big difference to our inferred radius for this source. So we've then essentially the NISA team have done a huge amount of work on background modeling. We took a look at this in a paper in 2022 led by my postdoc Tuomo Salmi, who actually used the new NISA background models on this same data set for 0740 and ran through it and got consistent results as the joint fitting with XMM using the NISA background estimates. So that's now really reassuring that we can actually model that successfully. Didn't change the inferred mass radius contours, which is great. So coming back essentially onto here, basically here we have basically the two mass and radius measurements so far that have been published coming out of the XPSI code. Just for comparison, and apologies for the slight jump in where the axes are, I couldn't quite get these to line up. What you're seeing here are the inferred credible regions for the Miller et al. Analysis from the Maryland-led team. So you can see essentially for 0030, very, very consistent and similar in size in terms of inferred mass and radius. For 0740, we're very, very similar lower edges. In general, the Maryland team's inferred credible regions for this source are larger, but there's quite a lot of discussion in the papers as to why that is the case. For example, I mean, one very simple thing in terms of radius prior, in our analysis, we cut off at 16 kilometers. Maryland team allow that to go out to 25 kilometers, so they have more prior space out there. We made some different choices in terms of channel cuts, which actually seems to make quite a difference at the upper end. So I think we now at least understand the sources of those differences, basically, but at the lower end, basically, we agreed very, very well once we figured out how we were both dealing with calibration uncertainty in modeling XMM. And I can come back onto that if anyone wants to discuss that in more detail and what the differences are in the analysis methods. Right, long term, of course, what you want to do is you want to take your mass radius posterior distributions, you want to take your favorite equation of state model, whatever that is, you want to take the gravitational wave data as well, you want to take any lab data you're interested in, and you want to infer an equation state, which is then the next phase in the analysis. If you want to do that, all of our mass radius posterior samples from our team and also from Cole's team are on Zenodo repositories associated with both papers. Go through the README file and you will find all of the things that you want in there in order to apply them to your own analysis, and also contours to plot these mass radius regions. You can then do a second stage of Bayesian inference to get an equation of state and hence a mass radius relationship. This is something that we also did, basically working with the team at TU Darmstadt. And for example, you can infer a mass radius relationship, something like this. And what you will notice in most of the inferred mass radius relationships is that they're very narrow compared to our actual mass radius measurements that we make. And a lot of that is down to the prior distributions on those equations of state. And we are still not at the stage, either with NISA or with gravitational waves, where we are, really pushing, a long way beyond what the priors are telling us and becoming fully data dominated yet. But hopefully that will change as we start to get better results. So speaking of better results, what is coming next, basically for all of our sources? So starting with the very high mass pulsar, the 2.1 solar mass, heaviest neutron star that we know. First of all, we have been looking at one of the aspects of our models, which is the atmosphere modeling. In the previous analysis that we did, we mostly assume a fully ionized hydrogen atmosphere model because that's the best physically motivated model that we have. However, different atmospheres, if it were helium, for example, or there were partial ionization at play, or some kind of weird return current heating that's a little bit different, could affect the way that the atmosphere beams radiation. So again, Tuomo Salmi, my postdoc's been looking at this in a lot of detail, having done some work on this during his PhD with Yuri Patanen. So he's been remodeling with different atmosphere models to see if it makes a difference. The good news for 0740, because of the geometry in parts of looking along the equator, doesn't really seem to matter particularly what kind of atmosphere model you choose, does not affect your outcome, which is really, really nice to see. And that's a paper that should be coming fairly soon on the archive. We also, of course, are gathering more data. I mean, this is a fantastic source. The more photons you have, in theory, your uncertainty regions should shrink, basically, and there's a nice relationship that predicts how that should go. We have a bigger data set already, more data than we've published. The analysis of that is largely finished, basically, so we're now doing all the collaboration cross-checks on that. And indeed, we can expect to go, I think, from about plus minus 10% contours, at least to plus minus 8%, basically with the update that's coming on that new data set, which is great. And then we are going to continue, as long as NICER is flying, we will continue to build up more data on that source. What about the one at the bottom? 0030, second brightest source for us, the first one that we published, no mass prior ahead of time. So having done all the analysis on 0740, there are a whole bunch of things we realized we would like to do for this source again. Again, atmospheres is something that we wanted to go and look at. For this source, your atmosphere assumptions, it seems, can make something of a difference. Now, again, we still think fully ionized hydrogen is physically the most likely, but indeed, if you did have a different atmosphere, it could actually affect your inferred mass and radius for this source. So that's something we're going to be flagging, basically, in this new analysis that's coming. We have also been doing testing of our pipeline. If we had started out with simulation where we generated data for a spot and a nice long crescent, would we have recovered it? This is not something we'd actually tested in our original simulation paper that looked at some of these things, but we're now doing parameter recovery simulations with more complicated geometries. And the good news is we do tend to recover things the right way, even for these complicated patterns. That's a paper led by my postdoc, Serena Vinciguerra, again, hopefully coming onto the archive very soon. Then, of course, we've got more data sets and more understanding. We have now a much bigger data set for this source. But before we moved on to analyze that, we actually decided to go back and reanalyze the data set we already published with much higher sampler resolution. This is something that we learned from doing A740, that it was a good idea to test this more. We had to reprocess this as data because the instrument response understanding has changed slightly as well. And the good news is that if you run through the reprocessing, you analyze the NICER data again, you end up with consistent results to last time, which is rather nice. But things get complicated when you now include background constraints on that old data set. And it turns out that 0030 has several possible solutions. Now, we picked out perhaps the most likely one last time, but this is a multimodal problem in terms of probabilities. So it looks like there are several different possible solutions. They would have different geometries, potentially different mass and radii coming out of them. And the background helps to push you, once you put your background constraints in, helps to push you in a certain direction. So I expect this one to move, basically. I'm not going to tell you which direction it's going to move in yet, and you may even get a couple of potential solutions. Basically, this is a paper that we're finishing up right now, essentially where you have a couple of potential solutions of different radii, but with very, very different geometries. We've done that as a baseline for the new, much larger data set that is coming, that we're now starting to analyze, and we're putting all of our computational resources into analyzing that bigger data set. But this one is complicated, doesn't have the mass constraint, but we now have fantastic background information, and that helps to cut it down. Of course, probably you would now like to know what's happening with our brightest source, and that is the next one, essentially, that the team will be publishing. So from the XPSI team, it'll be led by my PhD student, Debashi Chowdhury. This is a lovely source. It is a 1.4 solar mass pulsar. It's in a binary radio pulsar, so we know the mass very, very precisely from that, and distance and inclination to about plus minus 3%. So very tight mass constraint. We have a fantastic data set from it. It's annoying because there's a very bright AGN in the field of view, so you have to view it a little bit off axis, and getting constraints on the active galactic nucleus has cost us a bit of time. And because the data set is so beautiful, there are all these little features that you want to try and fit in it when you do your modeling. So we've had to go to some quite complex surface pattern models in order to try and explain this one. However, we do now have a solution, basically plus minus about 6% on the radius from this first data set. And again, that is still growing. We're now again finishing collaboration cross-checks, making sure that we have consistent results, and where we don't, that we understand everything. But basically that one is going to come and it will lie somewhere essentially along this line in mass radius space. So hopefully in the fall that will come out. We also have 4 additional sources that we're taking data on. 2 of them have masses, one at 1.9 solar mass, and another one for which the mass is not yet published. We're doing a whole bunch of additional cross-tests and simulations within the collaboration as well. So in the end, NICER will deliver 7 sources, you know, from I guess 10%, plus minus 10% at the outside, to some that will come in a lot tighter than that. And I'm going to finish, if I can just sneak slightly over the half hour, with a sneaky pitch for the next generation of missions to do this. We are putting together proposals, and particularly for the American audience, I think StrobeX will be the one of interest. It's a NASA Pro class proposal that we'll be submitting basically in response to the current probe call. It's a large area X-ray spectral timing mission. So basically kind of mega NICER, but also going up to kind of harder X-ray energies. And the reason we want to do that, so I can just show you the comparison of effective areas. NICER is shown here in green, effective area and energy. StrobeX will be the combination of these 2 pink lines. So basically much, much larger and also extending to much higher energies, because we can then do pulse profile modeling on accreting neutron stars as well. So we have a whole different class of neutron star. What we think we might be able to achieve by doing that is shown in very, very rough scheme here. Again, these are 95% credible regions that I'm showing. These are the current results that we have for NICER, again from the XPSI code. This is what we think might be achievable with something like StrobeX. We would have 3 different classes of neutron star that we can cross-check against each other for systematics, more stars with mass priors as well. We'd aim for an initial survey that would give us about plus minus 5% on a whole bunch of sources, cross-check any modeling systematics, and then do deep observations on about 6 sources to try and hit a plus minus 2%. Again, these are 95% credible regions for the most promising sources. So that is where we're trying to go basically over the next few years, building on the legacy from NICER. And I will stop there, take questions and any discussion points that anyone would like to go through.
Great. Thank you so much, Anna. Do we have any questions for our speaker? Please raise your virtual hand. While folks are thinking, I was curious. So you had mentioned about that, what's next for the brightest source. And you said that you had to go to some more complex surface modeling. Could you say a bit more about that, and what particular is requiring that? And is this something that would be necessary for other sources if the data was as high quality?
Yeah, so this is an interesting one. So basically what you find for this particular source is, if you start, for example, so with 0030, just to give you some idea, we started with, you know, super simple model, 2 hotspots opposite each other. Yeah, terrible fit to the data, beyond dreadful. Okay, so forget that, doesn't work. You can then go to a slightly more complicated model of 2 single temperature hotspots where you allow them not to be antipodal. And again, the fit doesn't look terrible. If you just look at the residuals between your best model that you find, your best model parameters and the data, there's nothing in there that you would flag and say it's bad. What you can say is, if I go to more complex models like this spot and the long arc, it's better. It's better in terms of maximum likelihood, it's better in terms of evidence and so on. So you pick the optimal model that way. But just on the face of it, if someone said to me, actually, it's just 2 circular spots and you have to cut your model space there, it would be fine. I mean, there is nothing in the data that would make me worry about doing that. If you do that for A437, you can't stop at the simplest one. There are features in the residual still that are not great. Your inferred background, for example, ends up coming out pretty bad. So there are things in there that you would look at it and go, ooh, it doesn't work. And once you put background constraints in there, it really cannot fit the data at all. So that one, the simple model just doesn't cut it. And once you take into account things like background constraints. And again, I think for J0030, that will also become more of a case as well. What you want to get to ideally is the point where adding more complexity doesn't shift things around. And I think as we put in background constraints and other constraints, that will eventually stabilize as well. And we now know how important the background constraints are as well. But yeah, basically with A437, you can't stop at the simplest one. just doesn't cut it. In order to get a good explanation for the data with the background constraints and knowing what the AGN is doing and all the information we've been able to gather. I mean, I should say this started as Devashi's master's project and it's still going for a PhD because it just got harder and harder to do. But essentially, once you put all that in, you find that you need a relatively complex surface pattern in order to settle on something that then stabilizes.
And I guess by a similar token, so for the ones that can be fit with a simpler model, if you do go to a more complex model, I mean, like you said, is there stability there, or I imagine you might see some degeneracy if you have some additional, knobs to play with there?
Yeah, so for 0740, we did try it. We did the simple model, all looked fine. Again, the data quality are not awesome. But we also tried the more complicated model, for example, that we had done for 0030. And because within that complicated model space exists also the simpler ones, that was the solution it favored. It didn't want to go to some big extended thing. But again, that's a very constrained source, good constraints on the background, good constraints on the mass distance and inclination. And then, it didn't matter. We could allow it to have a more complex model possibility, but it didn't want it, which is really reassuring. And my hope is that eventually, once we start piling in background constraints, the same will be true of the other sources as well.
Great. Now I see a hand from Dake. Please go ahead.
Thank you for this very nice overview. So I have perhaps two questions if time allows. So the first one concerns, so have we learned anything new about the hotspot physics? For instance, is there a way to test, whether stationary and, what sort of perhaps plasma physics could give rise to them just from the nicer observations made to date?
So you said for the plasma physics and for the magnetosphere?
Yes, for instance.
Yeah, so basically, I think this is actually one of the coolest aspects of the results. Again, the only way that the magnetic field appears in our calculations is by the shapes and locations of the hotspots. There's no magnetic scattering in there. They're low magnetic field sources. We're literally just making a map of where the magnetic polar caps are and the kind of shapes they have. So there are a large group of pulsar theorists now taking this, thinking about the magnetospheric physics and saying, does it make sense if this is the pattern at the surface? For example, can you still explain the radio pulsar emission and that pulsar profile? Can you still explain gamma ray pulsar emission? Because some of these also emitting gamma rays. Is the magnetic field likely to be stable? And we had a whole conversation in the collaboration about whether it, the curve that we found for 0030, the arc, was it a smiley face or a frowny face? And which one was consistent with theory? And we've been asked, how much wiggle room is there in what you infer? And we're trying to give the theorists an idea of what's possible before the model is just so terrible that you wouldn't want to use it. Ultimately, what we'd love to do is take first principles magnetospheric models constrained by radio and gamma ray as well, and use those as priors. Basically, rather than at the moment we allow everything to be a little bit free, but certainly we can modify our prior space to take into account any constraints. Essentially, they can throw at us. In terms of, again, plasma and atmospheric physics, again, that links in here as well. But so far, the fully ionized hydrogen model is holding up pretty well there.
So my second question is about the facts of the improved background knowledge. So just by a naive estimate, like the black body, I would imagine like knowing better the background would perhaps reduce the infrared radii, but you mentioned that the bond can move either way. So could you maybe elaborate?
Yeah, it can. So it also depends on the geometry. But basically, so yeah, it's not straightforward that having this much background going up or down would always change things in a certain way. Because, for example, it depends also on, what angle are you looking at the star? Basically, so the direction it moves for 0740, where we're very constrained in how we're looking at it, is not going to have the same effect as 0030, where we don't know the angle. So there are multiple different ways of creating an unpulsed component in there, for example. So in fact, you can move things in different directions. But yeah, basically it's telling you, how much of that unpulsed component is coming from something that isn't spot.
Okay, thank you.
I see a hand from George next. Please go ahead.
Yeah, thank you. So thanks so much. That was a great seminar. So I had two questions. The first of all already got asked, and you beat that one to death. So and I learned a lot. The second one is just more of a technical thing on Strobe-X and I guess on NICER as well. Strobe-X is sensitive to higher X-ray energies. I didn't see how far out it goes. It looks like a border 100 keV. Is that right?
Yeah, so I kind of stopped worrying about it at about 30 keV, but indeed there is basically energy performance beyond that as well. So Strobe-X have a website. There's a white paper, Ray et al., which would cover the very high energy performance as well, if you're interested in that. And it has an all-sky monitor on there as well, to monitor transient sources too.
And what is the effective area of Strobe-X compared to NICER?
So several square meters is the goal. So basically, yeah, so we're aiming ideally, so several square meters as opposed to, much less than a meter for NICER.
And then what about spectral energy resolution? Is that comparable with NICER?
Yes, so it has to be good, not just for the dense matter science that we want to do, which of course is NICER's thing of having good spectral energy resolution, but they also want to do a lot of black hole science for things like reverberation mapping and so on. So basically the black hole case is also, in fact, I think that's the main driver for the spectral energy resolution, not anything that we're doing. We have a lot of discussions actually about whether our spectral energy resolution is almost too good. Should we just be binning things, and would we lose anything if we did that?
Thank you.
Great. I see there's a question in the chat from Madhapa Prakash. If you'd like to unmute and ask your question, otherwise I can read it for everyone. So how does one pin down the sizes of the hotspots?
Right, so hotspot size and central location, any overlapping parameters if your hotspots have dual temperature and the temperatures and so on, those are parameters in our model. And we make sure that things don't reflect and we make sure that things don't overlap. But basically, yeah, hotspot angular radius is a parameter in the model. So it is one of the parameters for which we obtain a posterior distribution. Now, so when you see the maps that I showed with this is where the hotspots are, of course, that's not necessarily the map because there's a certain probability of locations, but that's really hard to show. One of my postdocs had a go at trying to make a movie of all the places the hotspots might be, and it kind of blurs your eyes after a bit. But in principle, you can say it's most likely to be within this region and about this size. So yeah, it falls straight out of the modeling as well.
Great. Hopefully that covered it for Kosh. Any other questions for Anna, or any final points of discussion? I don't see any additional hands, so let's thank our speaker once again.
Thank you. And if anyone is interested in getting involved in the Strobe-X science case, I would be very happy to have more nuclear physicists basically involved in the discussion, and anyone who's interested in multi-messenger and transient science and so on. So if you are interested, please just drop me an email. Tom Macarone is the science PI, and Deepta Chakrabarti and I are the deputy science PIs. So we'd be very glad to have extra inputs into the science case and into the science book that we're preparing for November.
Excellent. Thank you so much.